Sorting is a basic task in computer science. It's been heavily studied. It was probably one of the first problems to receive really significant kind of research efforts or formal study. It's still the topic of a lot of study. People are coming up with new sorting algorithms all the time. So that being said, there are a lot of sorting algorithms. I'm going to introduce sorting with a method called Insertion Sort. It's pretty simple. It's also still useful in some special cases, but it illustrates the problem and how to solve it pretty well. So let's see here. So of course the goal of sorting is, still getting used to this tablet, yep. Let me put out some numbers. So let's say I have this sort of array or list of numbers, or really anything that's comparable. We want to take it in whatever order it happens to be given and produce a sorted order array / list. So starting with the smallest numbers and ascending up to the end, the largest values in the back. Now, there's a lot of different ways to accomplish this goal. Insertion sort, now if I kind of draw out my array here, what it's going to do is it's going to keep the front part of the array sorted. So let's say this is the sorted part as it's working. Then we have our next value here. It's going to look for where this should go in the sorted portion and move values down accordingly. So this is how it works. This is one strategy. Of course, there's a lot of different methods, and how an algorithm maintains like a partially sorted list is basically one of the key differentiations between them. But yeah, for insertion sort, essentially it's going to take the next value as you're iterating through the list or array and go back towards the front and look for where does that value go. So it's going to keep moving it further towards the front the smaller the value is. So let's just scroll down and give myself a little more space. Let me work through this. So I'm going to drop my array here. Now over on the side, I'm going to need I. That's going to be my index, the current value we're on. Put C for the current value. We're going to essentially copy values out of the array, put them there, and put them back. And of course, there's some little adjustments you can make to kind of reduce the number of operations involved. I'm trying to keep this as clear as possible. So we're going to start at 0. So that means there's nothing sorted. We're here, right? That's my little arrow. Whoop. Okay. This is essentially a special case. We can think, oh, we'll put 5 into our current value. Since there's nowhere to go, it's just going to stay there. We can't shift it over to the left at all. So now we're going to assume this part of the array is sorted with this single value in it. Now we'll move our index over here. So at 1, current values, put 3 here. Maybe I'll cross that out too. There we go. So when I put 3 into C, what I should do is just remove it from the array. Sort of, let's just say logically speaking, you don't literally need to do this, but we're going to remember what C is. And now compared 3 to 5. Well, 5 is greater than 3, so we're going to move it here and take it out of here. Now we're at the special case where there's nothing to the left. So here we go. We'll put 3 in there. Great. So that concludes that that iteration. We'll move on to 9. All right, spot 2. Remember 9. Now we're going to compare 9 versus 5. 9 is greater, so there's no need to move it. So you can start to see this sort of rule emerge as we compare our current value versus the value to its left. We keep moving it down so long as it's less than the value to its left. So right away, 9 is greater than 5. We don't need to do anything. So that concludes that round of iteration. So let's move our index down here. Now the current value is 1. So we can see, I'll just clear this out. We copied 1 over into our current spot, C variable. Now 9 is greater than 1, so we'll move 9 down. Now the empty spot is here. We're going to compare 1 versus 5. 1 is still smaller, so we'll put 5 here. Now our empty spot's over here. Now we compare 1 versus 3. 1's still smaller, so we put 3 here. And make this our empty spot. Now we're at the front of the array. So there's nowhere left to go, so that's where 1 must go. Ta-da! Now that concludes that round of iteration. What we're going to do is advance this to the end. So our current, there we go, our current index is 4, the current value is 6. So we're going to take it out, we compare it to 9. Well, 9 is greater, so we'll put it there. Now we're going to compare 6 versus 5. Well, 6 is greater. So now that rule of keep moving left till we find a smaller value, that's met. Put 6 in here. That concludes that round of iteration, and we are done. We're done, yay. So that's insertion sort in a nutshell. Now let's go take a look at some code for this. I've written this up in Java. So if I transition over here, I have it already completed. Unlike my other videos where I can sort of live code it. So first things first, you can see here, ignore this part. This is just for printing, and I'm going to show you what it looks like as I run through it. But so this is the outer loop up here. This is going to go through each value in the array, and then for each value we're just going to look and see how far to the left we should move it. Here, instead of C, I called it current, a little foreshadowing there. And then I need another index J, because that's going to be the index we use as we move the value to the left. So this outer loop's plain, we're just going to copy the value at I into that spot current. We're going to set J is equal to where to the current index, and then we're going to, in this while loop, we're going to move to the left. That means decreasing J. We're going to make its index smaller and smaller, so long as the value to the left is smaller. And well, this first condition is actually while there's still a spot to the left. So if we take 1 off of the index, if that's still greater than or equal to 0, because 0 is the first index, we can keep going. But as soon as that's terminated, or as soon as that condition's not met, then this loop's going to terminate. The second part says, well, while the value to the left is greater than the current value, all we're going to do is shift the current value or the value at J to the right. So that's that empty spot I'm moving a value into. So I'm moving things to the right as I move to the left, and we do that here where we decrement J. Then finally, so what this is going to effectively do, this inner while loop, is move values to the right, just like I was doing by hand, so long as these values are greater than the current thing we're sorting for, the current value. And finally, once that loop's completed, there should be a hole, so to speak, at j where the current value should go. Then, like I said, all this is just fun printing things. So now, running through the same example down here, if I run the code, we'll see it does the same thing where it'll be at 5. There's basically nothing to do, so it's just going to print out the array after all the operations have worked. Now I move the 3, so you can see 3 started here. It just moves it all the way to the left as it should, which it's done here. Now we're at 9. That's the current value. It doesn't need to move at all. Now the current value is 1. It's going to move all the way down to the left. As we can see, this is the output of that iteration here. Last value is 6. It just needs to be bumped over 1. And that's it. That's insertion sort in a nutshell. One other thing, so if I jump back to this, we can think, the real question is, well, if we have different sorting methods, as I alluded to before, why do we have, why do you have different methods, and how would we compare them? Is it just a matter of like style or fun? No, there's different amount of time. So the time it takes, I haven't really covered this yet, is going to be about n squared in the worst case. So I say about n squared, that means if n is, the length of the array. So, and you can see that in the loop. We go through each value. We're going to do that n times, or the number of values in the array. And then for each value, we need to move it to the left. So basically the worst case would be backwards sorted order or something close to that, where we have to move everything every time to the front. So you can think for each number in the array, we have to move it basically almost the entire length of the array. So that's why you can say it's about n squared. So this whole about thing, we use, let me scroll down a little bit. We'd call this big O n squared. So big O means the runtime is about, the true runtime, t of n is about n squared, and the usually worst case. We can do best case and average case analysis, but we're typically concerned the worst case because I guess computer scientists are a bit pessimistic. Well, no, it's really because it's a stronger guarantee. It's very conservative. So this is called big O notation. This is starting to get into the heart of real computer science versus just programming. And we'll look at different sorting methods later that can do better than this. So that's insertion sort in a nutshell. Thanks for watching.